Okay, so I want to pick up where we left off last time, talking about the resolvent operator. And in particular, I want to discuss what I hinted at last time, which was the spectral decomposition theorem, and how you take an operator and decompose it into its spectral constituents. And then we'll show how the resolvent operator, which was the inverse of an operator, has an intimate relation with the idea of Green's functions, where the operator in question is not a matrix, but a differential operator. Okay, so that's where we want to go today. Let me remind you where we left off last time, which is that we had these projection operators that were these guys here, basically without the sum. So minus 1 over 2 pi I times the integral over gamma k of the resolvent of the operator A at lambda, and then I integrate over all lambda on that contour. All right, so this defined for us a projection operator, and we showed that it was a projection operator because it satisfied a relationship like this: pi pj is delta ij pj with no sum on the i's and j's. And what this meant was that when I equals j, we showed that p squared was equal to p. We calculated that explicitly, and I left as an exercise for you to show that in addition to this, that pi pj when I was not equal to j was equal to 0, so they were orthogonal to each other. Okay, so what I want to do today is do an example. Well, first I want to actually demonstrate the spectral decomposition of some operator, let's say A, in terms of the lambdas and the p's, the projection operators. And then we're going to do an example with a very simple 2x2 matrix, so you can develop some intuition for this. Any questions to start off with? Okay, so to start off with, let's suppose that we took our function f of a and set it equal to a, okay, for some operator a. And I want to deform the enveloping contour gamma, capital gamma, into the union of some small set, into the union of some small circles, little gamma I, that are centered on the singularities of the resolvent. So then, so we want to deform the integrating contour gamma into the union of contours gamma I. Then the following is true. Remember, we had this generalization of the Kashi integral formula. Well, this says that for f of a equal to a, that this a is 1 over 2 pi I times the sum over, let's say, I equals 1 to r of the closed integral over contours gamma I of, remember we had an f of lambda in the integrand. Well, this is just a linear function, lambda, r lambda of a, the resolvent, and we integrate with respect to lambda. Okay, now what I'm going to do is I'm going to add and subtract a set of lambdas, which I'm going to call lambda I. Okay, so this is equivalent to, this is equal to minus 1 over 2 pi I times the sum over I equals 1 to R of lambda I times the integral over gamma I R lambda of A d lambda plus integral over gamma I of lambda minus lambda I R lambda of A d lambda. So these guys, lambda I, are the poles in the lambda plane, the location of the poles in the lambda plane of the resolvent. Okay, and all I've done is I've added and subtracted a lambda I and a lambda I there, and then I've grouped them individually. Well, the first term, this guy here, okay, let me do this with a pointer. So this first term here, including this minus 1 over 2 pi I, is nothing but the projections that we've been working with to date. The second term here, including the 1 over 2 pi, is a new object, which I'm going to call di. So taken together, I'm going to say that this defines for me the following relation for A. Okay, so A is equal to the sum over I of lambda I pi plus set of objects that I'm going to call di. Okay. And in your exercise sheet, you'll notice that the last problem, I think, has the following result. So I'm going to remind you that this is an exercise, which I'm going to leave to you. And this was to show, essentially by induction, but if you have a smarter way of doing it, I'm all ears, that if I take this object di and I raise it to the nth power, then this is just minus 1 over 2 pi I integral over the gamma I of lambda minus lambda I to the nth power, or lambda of A d lambda, like such, right? And I'm going to use this relation now. So the point is, I can take this, I can take my operator A, I can break it up into this integral representation, where I take the integrals over the gamma I, and I can split that integral representation into two parts. One part is lambda I being the poles. And if you remember what we said about resolvents, where the poles of the resolvents are precisely where the eigenvalues of the operator A are. So these lambda i's, which are the poles of the resolvent, are nothing but the eigenvalues of the operator AI. Of the operator A. So I've broken it up into two parts. One is lambda times the projector, and the other one is this object di. Now I'm going to make an argument for the object di, because we've shown, well, I'm giving you as an exercise to show that di raised to the nth power just raises the lambda minus lambda I to the nth power in the integrand. Okay. Now let's make the following note. So now let's note that the following is true. The resolvent operator because of the structure, 1 over A minus lambda times the identity, only has poles. Okay, so we note that since our lambda of A only has poles as singularities, well, this means that if I raise di to a sufficiently large power, so I'm referring to this power here, if I raise it to a sufficiently large power, then the integrand of this di to the whatever, say m, will eventually become analytic, because what's multiplying it, this guy here, will cancel off the denominator, the poles in the denominator. Can you see that this is true?
Yes.
Good. So since the resolvent only has poles, if we raise di to a sufficient power, let's say m, then the resulting object di to the m will be analytic. Sorry. Then the integrand of di to the m will be analytic. Which will then imply necessarily that the integral of an analytic function over a closed contour is necessarily vanishing. So if I raise this di to a sufficiently large power, it'll eventually vanish. Okay. So the next point to note is that if A is in addition a Hermitian operator, then the resolvent of A can have at most simple poles. I'll do an example to convince you of this just now, but I would like you to take this as a given. There's a theorem in operator theory that says that if A is Hermitian, with respect to some inner product, then at most it can have, the resolvent of A can have simple poles. Well, simple poles means lambda minus lambda I is going to have power 1, which means that as a consequence of that, all I have to do is raise di to the power 1, which or rather that lambda minus lambda I times r lambda of A is analytic. And this in turn means that the di is necessarily 0 for all I. And this gives us what we call the spectral decomposition theorem. So the spectral decomposition of A then tells us that we can break up A into the following. So if the di's all vanish, this says necessarily that our operator A in here, if the di's all vanish, that means that all of this stuff vanishes, which means that I'm only left with this stuff here, or in this language, this first piece here. In other words, I can take my operator A and I can write it as the sum over eigenvalues 1 through r of lambda I times the projectors that we wrote. And this is what's called the spectral decomposition of A. So it's a very important theorem in operator theory or spectral analysis. For those of you who took the spectral analysis course in the first semester, hopefully you recognize this. Any questions?
Yes, I have one question. On the previous slide, if you could go back there, when we have the lambda minus lambda I to the n, and we are raising di to a sufficient power, is that sufficient power always going to be as great as n or less?
So n here was just a general n. I'm just saying raise it to some power, and what happens is that the lambda minus lambda I in the integrand gets raised to that power. So that's what I want you to show. Right.
So we couldn't raise it to a power such that we still have sort of non-analytic poles in the denominator, or it's causing it to be not analytic. If we,
I'm not sure what you mean by non-analytic poles.
Yeah, it's not good wording. What I mean is, if we don't raise it to a sufficient power, right, we won't be able to show that it's analytic.
That's right. So the di will remain. So the point is that I can kill off, I can always kill off di. Okay. So the point here is that I have this object di, right? Squared, all that happens is that the lambda minus lambda I in the integrand gets squared. Cube it, same with the lambda minus lambda I. Okay, you with me?
Yeah.
Right. So raise it to any power you want, and the only thing that's changing is the lambda minus lambda I in the integrand gets raised to that power. Agree?
Yes.
Good. So now my statement is the resolvent, the remaining factor in the integrand, only has poles by definition.
Yeah.
Right. And it has poles where the operator A has eigenvalues, so things that are the spectrum, right? So I can take the set of all lambdas and I can break it up into two parts. One I'll call the spectrum, and the other one is called the resolvent set. Okay. So the resolvent has poles when the lambda is in the spectrum. You with me?
Yes.
By the way we define the resolvent, okay? So that means that this guy, R lambda, can only have poles. So there's a whole bunch of other types of singularities that you can have in the complex plane, but none of them matter because the only type of singularity that it's allowed to have by its definition are poles.
Yeah.
So then the only thing that could possibly change is the order of the pole. Okay? So suppose I have this guy and it has poles of order 2. If I multiply this thing, which has poles of order 2, with lambda minus lambda squared, then the resultant thing doesn't have any poles. I've canceled off the poles in the same way that you would cancel off the poles when you try to calculate the residue at a pole, right?
Yes.
Right. So the point is, if I raise n, if I increase n enough to cancel off whatever the order of the poles in RA is, then the resulting object here is going to be 0. In other words, I can always find some value of some sufficiently large value of n, right? In this case, I call that value m, but I can always find some sufficiently large value of n to make sure that the integrand here is analytic, and then the integral of an analytic function is 0, so that the di will be 0.
Right.
Any
okay.
less than that, for any value of n less than the order of the poles in RA, and the di is going to stick around.
Yes. Okay. So that's what I was asking.
Yes.
Okay. So you can always raise it that high, such that you don't have any leftover.
Right. All I'm trying to do is make an argument that I can kill off the di.
Cool. Yeah, that answers my question.
Okay. All right. And the point is that if I consider A to be a Hermitian operator, then it's going to have simple poles, which means n must equal to 1, or rather m must equal to 1. You buy that, William?
I do.
Good. So that means that the di is going to equal to 0, which means that what I'm going to be left with in this statement here is that I'm expanding A in the sum over its eigenvalues over the projectors.
Yes, that absolutely makes sense. Yeah.
Good. So let's do an example then to build some intuition, okay? And I'm going to do a finite dimensional example here because, again, I'm only interested in building intuition. So, you can pick an example that has lots of integrals to think about, but let's rather not do it. Let me show you that this works with, the simple matrices that you've been working with since kindergarten. So suppose I have the following. Let's take A to be a 2 by 2 Hermitian matrix. So let's take A as a 2 by 2 Hermitian matrix. Okay, the most general such matrix will take the following form. And for it to be a Hermitian matrix, it can only be the following form. So the most general such matrix I can write down will have A11, A12 in the first row. And the second row has got to be A12 complex conjugate. Let me write bar down. Complex conjugate and A22. And the condition here is that A11 and A22, the diagonal elements, have to be real. Sorry. Okay, if that is the case, then I have a 2 by 2 Hermitian matrix on my hands. Whatever you want these independent elements, A11, A22, A12, to be, that's fine, as long as they satisfy this condition. The corresponding characteristic equation for this has got to be the determinant of this A minus lambda times the identity equal to 0. But this is a polynomial in lambda which you can work out, it says that lambda squared minus A11 plus A22 lambda plus A11 A22 minus mod A12, remember A12 can be a complex number, squared must equal to 0. So that's a characteristic equation. This has roots. Which I can solve quite easily because this is just a quadratic equation, and the roots are lambda plus or minus, which are a half of A11 plus A22 plus or minus the square root of A11 minus A22 squared. Just done some algebra here. Squared plus 4 mod A12 squared. Okay. Those are the roots of the characteristic equation. And given the roots of this characteristic equation, we can quite straightforwardly write down the inverse of the operator of the matrix A minus lambda I. This would be R lambda A, which is A minus lambda times the identity inverse. And this is just 1 over the determinant of A, just from what I learned from first year already, determinant of A minus lambda times the identity times A22 minus lambda, A minus A12 minus A12 complex conjugate, A11 minus lambda, which we can then write in terms of the roots of the characteristic equation as follows. That's just 1 over lambda minus lambda plus, the plus root, times lambda minus lambda minus, because I can factorize the characteristic equation like that, times A22 minus lambda, A11 minus lambda minus A12 minus A12 complex conjugate. So that's the resolvent, right? And that's how to calculate the resolvent for a simple 2x2 emission matrix. So now I have to distinguish two cases. So my claim was that if I have what I'm trying to show with this example is if I have a Hermitian matrix A or Hermitian operator, then at most I'm going to get simple poles, right? So now let's distinguish two cases. Case one is if lambda if lambda plus and lambda minus are distinct, in this case, clearly I only have two simple poles. And my statement holds trivially. On the other hand, so I'm looking here, right? All of this stuff is fine. To read off the pole structure, I've got to look at this fraction here. So if lambda plus and lambda minus are distinct, then indeed I've got two simple poles. Right? What happens if lambda plus and lambda minus are coincident, and let's say they take a value a, right? So now I will have lambda minus a times lambda minus a, or lambda minus a squared. So it looks very much like the resolvent has a double pole. But this is not true. Right? How? Because we note the following. When lambda plus and minus are both a, the only way this root equation holds is if the following is true. If a11 and a22 are equal and they're both equal to a, and a12 is equal to 0. So the only way that I can get two coincident poles is if the diagonal elements are both equal to a, and the off-diagonal elements are both equal to little a, and the off-diagonal elements are both vanishing. So this means that the resolvent r lambda of a is equal to minus 1 over lambda minus a times the identity matrix, the 2 by 2 identity, because there's precisely one factor of lambda minus a that will cancel out. And again, the moral of the story is we have a simple pole. Okay, is that clear?
Yes.
Great. All right. Very good. Of course, you should ask the question. Yeah.
On that line, but notice that A11 is equals to A22 equals to A. What is A? I think I got lost there. What is that small a?
Okay, so I said here, I'm distinguishing two cases, right? In in this equation here, I'm interested in the pole structure of this guy here. You with me?
Yes.
Good. So the place to go and look for where I've got poles is precisely here. All right? So I said there are two cases that we can distinguish. One is if lambda plus and lambda minus are different things. You with me?
Yes.
Okay. So if lambda plus and lambda minus are different things, then clearly I've got two poles and they are both simple.
Okay.
Okay, so they're both raised to the power 1. Okay?
Yes.
So the second case is the opposite of this. What happens if lambda plus and lambda minus are both equal to each other? And I'm going to say, suppose they're equal to something called little a. Okay?
Yeah.
So in that case, this becomes 1 over lambda minus a squared. That factor. Do you agree with that?
Yes.
Right. So that looks like a double pole, which contradicts what I said. If A was Hermitian, then its resolvent can only have some simple poles. But now I just showed you something that looks like a double pole, because I said if you want to talk about the pole structure of the resolvent, here's where you got to look. But this stuff also contains information. It contains information because if I go back to the root equation, this equation here, right? And I set lambda plus and lambda minus both equal to A. And I ask what values of A11, A22, and A12 will satisfy this equation, right? Well, these two equations. I will find that the only values that will satisfy it is if A11 and A22 are both equal to the same A here, and A12 is equal to 0. Are you with me?
Yes, yes, yes.
So let's take that and plug it back into this matrix here. I get A minus lambda and A minus lambda, right? I get a 0 here and a 0 here. Okay? So I can pull out a factor of A minus lambda and A minus lambda, and I'm left with 1001, and a factor of A minus lambda in the numerator.
Oh, okay, and then
right? So that cancels with one factor in the denominator, and it leaves me with this minus sign here.
Okay.
So indeed, I still only have simple poles.
Yeah, makes sense now.
Okay, so this was a very straightforward, simple example. Okay, I didn't demonstrate it, you know, in the most general case we can, but I don't think we need to, because we're just trying to build up some intuition for how to think about these things. But of course, you know, at this stage, you really ought to ask, what the hell does this have to do with Green's functions? After all, the title of today's lecture is Green's functions and resolvents. Okay, so somehow they should have something to do with each other. So, what question?
No.
Okay. So, the question I have is, what does all this have to do with Green's functions? Exactly. Well, there are two things that we learned so far. And there are 2 points to note. They're just observations at this point. We're going to make them more precise just now. One is that Green's functions are inverses of differential operators. Green's functions are inverses of differential operators. The second thing that we've just learned is that the inverses of operators are best understood in terms of resolvents. And so indeed, I would expect that Green's functions then must be related in some way to resolvent operators. So let's try and make this relationship more precise now. So to make this precise, I first have to make one more statement. So this is an important statement that we have to keep in mind. And it is a statement that an operator will only have an inverse if and only if 0 is not one of its eigenvalues. So think about a matrix. If I want to find the inverse of a matrix, I very importantly need the determinant of the matrix not to vanish, right? But if one of the eigenvalues of that matrix is 0, and the determinant is the product of the eigenvalues, then the determinant is going to vanish, and I'm not going to have an inverse. Is everybody with me? The logic of this argument needs to be clear.
Yep.
Right. So an operator will only have an inverse if and only if 0 is not one of its eigenvalues. Conversely, if an operator has an inverse, then 0 is not in its spectrum, which means that it has to be in its resolvent set. Are you with me there? Remember I said I could take the set of lambdas and break them up into 2 parts. One is the spectrum and the other one is the resolvent set. The resolvent set is a set of lambdas that I use in defining the resolvent, 1 over a minus lambda I. Okay? So the statement is the following. 1, an operator only has an inverse if and only if 0 is not in its spectrum. So an operator only has an inverse if and only if 0 is not, let's not squeeze it in there. If and only if 0 is not in its spectrum. Okay. The second statement is the converse of this. If T inverse exists, then 0 must be a resolvent set of T. Is everybody with me? And if this is the case, then the resolvent of the operator, let's say let's say T, the resolvent of the operator T at lambda equal to 0, which I'm going to call R naught of T, is just L minus, T minus lambda inverse at lambda equals 0, which is just T inverse, or what we were calling the Green's function. So that's the connection between the Green's function and the resolvent. Is everybody happy with that? Okay, so I'm going to stop here, having made this connection between the resolvent and the Green's function, and we'll pick it up on Monday, where we'll look at the specific case of the operator T being a Sturm-Liouville operator, and show how this corresponds to the eigenfunction expansion of the Green's function, which we've noted before already. Any questions? And then I'll do an example where the operator is a simple second order derivative operator. with Dirichlet boundary conditions. Where I'm building to this, by the way, it'll probably take us 2 lectures to get to, but where I'm building to this is where the particular Hermitian operator that we're interested in is the Hamiltonian in a quantum system, and I'll show how we can solve essentially the Schrodinger problem using resolvents. So it's quite a beautiful set of arguments to get us there, and it'll take us a little bit of time, but it's definitely worth the journey. All right. Any questions?
Nothing from me.
Good. All right. So let's stop here.